Welcome to the introduction of quantum information. The aim of this course is to communicate a basic understanding of the key concepts in quantum information and computing, to understand how these concepts come about and their consequences, as well as to prepare you for studying more specific and advanced topics in the field. To facilitate the broad spectrum of learners who could be interested in this course, we try to design it in a self-contained way. We will first give a general perspective and a brief historical account in the field. Then, we record some of the fundamental elements of quantum mechanics in order to proceed to the discussion of quantum information. We then illustrate a few key and early developments that are important as well as easily accessible. By going through this course, together with the course on Introduction to Quantum Computing, hope we can help getting you ready for a more in-depth journey on the understanding of other specialized topics in quantum technologies and their applications. So, why do we study quantum information? The first motivation comes from the foundation of information theory. Information is carried by actual physical systems, and the communication and computation of information relies on real physical devices. This is well summarized by the phrase, "Information is physical." In the classical world, we learn that information is registered and processed on physical systems such as computers, electromagnetic waves, brains, DNA strings, neurons, etc. The rules governing these classical systems is intuitive to our understanding of information. Now we know that the universe are, in fact, governed by quantum mechanics. This quantum mechanics offers a richer description of nature, such as superposition and entanglement, which are counterintuitive to our classical understanding. Information is physical. Thus, this physical theory requires a revision to the classical theory of information. And this led to the birth of quantum information theory. The second motivation comes from the foreseeing hardware challenge. Technologies for smaller and more efficient computer chips are developing with an amazing speed. The Moore's law predicted that computational power would double at constant cost, roughly once every 2 years. This is approximately true since the 1960s. The current technologies of chip fabrication will soon reach its limitation as smaller and smaller electronic devices are required, and quantum effects unavoidably becomes relevant. Other than the hope for a breakthrough in the technology of computer chip design that eliminates the quantum effects, there is another possible solution to the problem, making use of quantum properties of small scale for computation directly. This certainly requires the understanding of quantum information and quantum computing. Thirdly, the research on new materials, understanding of chemical and biological processes, can be much advanced if we can simulate these quantum systems effectively. However, given the complexity of this kind of many-body quantum systems, it is fundamentally impossible to simulate them using the current classical computers. The idea of quantum simulation rises, that is, why don't we use one quantum system to simulate another quantum system? The fourth motivation came from the fast development of experimental techniques. Physicists understand better and better how quantum systems evolve and interact with each other, as well as how they interact with the macroscopic systems. Since 1970s, single quantum systems can be controlled quite precisely in laboratories, such as trapped atoms and ions in lattices. These experimental techniques kept improving through the years. Well, how can we make use of these experimental developments and transfer them into technologies? Quantum information came to the spotlight. Last but not least, starting from the early 1980s to 1990s, the computational power of quantum systems is recognized through a few very important developments. Ever since, interest in the study of quantum information grows rapidly. The recognition of computational power of quantum mechanical systems is one of the key motivations for studying quantum information and quantum computing. Now, let's go back in time to talk very briefly about some of the key developments in the 1980s and 1990s. In 1982, the no-cloning theorem, independently derived by Wouters and Zurek, as well as by Dix alone, resolved the question on whether it is possible to signal faster than light using quantum systems. The answer is no. Superluminal communication is not possible, and Einstein's relativity is not violated. David Deutsch, starting in 1985, formulated the notion of a universal quantum computer. He also showed that it is possible for quantum computers to solve certain problems more efficiently than classical computers. Shor's algorithm in 1994 pushed the field to the spotlight enormously. The two problems, prime factorization and discrete logarithm, were widely believed to have no efficient solutions on a classical computer. Shor showed that quantum computer can provide exponential speedup in finding the solutions. Grover's search algorithm in 1995 further expanded the interest in the subject of quantum computing. Other than the developments by Shor and Grover on the gate-based algorithms, other people are following the idea which believed to be first suggested by Feynman in 1982, that is, to simulate quantum systems with quantum systems. Of course, the theory of quantum information, as its name suggests, does not only build on the theory of quantum mechanics, but also relies on the theory of information. The foundations of the modern theory of information and communication has been well established as early as 1948 by Shannon. He formulated the mathematical definition of information. He studied two fundamental problems related to the quantum communication of information: physical resources and robustness against noise in the channel. He also showed that error-correcting code can protect information from noise. Quantum information theory inherited much of Shannon's theorem and tried to find its quantum analog. Two of the subjects that developed successfully from this are quantum error correction and quantum cryptography. For the protection of quantum information against noise, CSS codes was developed in 1996, named after Claude-Bank, Shor, and Stein. This code is recognized as an early example of the stabilizer codes, which has great impact on the development of reliable quantum computing. for the protection of classical information. In 1992, Bennett and Weissner came out with a scheme that can communicate 2 bits of classical information using a single qubit, the so-called superdense coding. Building on Weissner's earlier work, Bennett and Brassat in 1984 proposed a protocol that allows the secure public key distribution between 2 parties without any compromise. This is referred to as the BB84 protocol. Since then, many quantum key distribution codes has been proposed, including ACK91 and continuous variable QKD. QKD gets even more attention after Shor showed that the classical public key distribution using RSA would no longer be secure if quantum computers become available in the future. Other than the developments in quantum information theory, there has also been tremendous efforts in building quantum computing and communication hardware. Proof-of-principle experiments have been reported. However, it remains a great challenge to scale up those early-stage quantum computational devices and to mitigate noise for reliable and accurate computation.